Alrighty then. So to start off, this particular calibration has already been set up perfectly. If you look at my left strip chart, I've got a mix 1 vertical. Right strip chart, I've got channel 6 vertical. And in my Lysigue, we're looking at channel 1. So that has the 100% whole signal rotated to 40 degrees, which is typical for most bobbin coil exams. Some places set ProMotion horizontal, but that will put your signal from the 100% whole to between 35 and 40 degrees. Both of them work fairly well. Usually data is a little bit cleaner when you set noise horizontal, but you have to refer to your code requirements to see what is allowed. That's guess angle, I don't want that. So again, it's already been calibrated. So there's the 100%er, there's the 60%er, and there is the 20% flat bottom holes. If I go down a little bit further, we're going past the tube support plate signal. And then here we have a 20% wear scar. Then we have a 40% wear scar, and then we have a 60% wear scar. So that's all the flaws. Now I already constructed a 2-channel mix for differential, which is I think a channel 1-5 mix, 400-100 mix. And then for mix 2, I believe I have a 4-6, which is a 200-100 absolute mix. Now when you construct calibration curves for sizing things like OD pits, oftentimes a phase versus depth calibration curve will be constructed. Because this is phase analysis, and we know that eddy currents penetrate the material at different times at different depths. The further you go into the material, the longer it takes your eddy currents to penetrate to those depths. And what we've noticed over the many decades that we've been studying eddy current is that the eddy currents that are deeper in the material will output signals that have more phase lag. So again, we set the 100%er to 40 degrees, and then we just see where the signal from the 60% flaw lies on the Lysigue. So if we scroll to the 60% flaw, it's got more phase lag. It took more time for the eddy currents at that depth to be disrupted. Similarly, when we go a little bit further into the material to the 420s, which are placed around the circumference, we have even more phase lag. That's probably about 140 degrees-ish. So clearly we can see that there's a difference with the phase angle for the different depths. So what we can do with a phase versus depth calibration curve is tell the software that the 100% signal that sits at 40 degrees, well, it's 100%. That's what we input into our sizing curve. And then for the signal that comes up here around 100 degrees, we're going to tell the software that that's 60%. Then we're going to scroll down here to the signal from the 420s around the circumference, about 145 degrees. We're going to tell the system that that's 20%. Now where we do that, there's a feature here, analysis curves. Now, I've already constructed these curves, but how you construct them is as follows. For this particular instrument, here I have 400 kilohertz in the Lysigue. So I'm going to go and place my cursor position on that signal. And I'm going to hit max rate. That measures the flyback angle here. And I can see that it's 40 degrees because that's the way I set it. And let's look at the angle, 40 degrees. Then we'll go into analysis curves. Now, I can go over here and select between an angle curve and an amplitude curve. But for now, we're going to focus on the angle curve. And we're working with channel 1. So the 0 degree point automatically defaults to 0%. And in this particular software, it just automatically assigns 20 degrees as 50%. Now that would be the ID flaw portion of the curve. We don't have any ID set points in our calibration standard for this tube anyways, so we'll just go with the default. Now the 40 degrees, that's where the 100% signal lies. I had already toggled this into 100%. But let's say we didn't have 100% and we only had a 99%, or I could change that down. But as you change it, you can see the shape of the curve changing. But we know it's 100, so we're going to go and set it there. Now let's go back and we'll go look at the 60% flat bottom hole. We're going to measure the flyback angle, 100 degrees on channel 1. So we go into our analysis curves. Again, I had already set that to 60, but if our as-built dimensions on our cal standard were something different, like 55%, I would just adjust that number there. And therefore, when I go here and measure that, it's going to say 55% because that's what we trained the system on. But since I know it's 60%, I'm going to go back into the curve, excuse me, and I'm going to change this back to 60%, where it belongs. Now we're going to go to the 20s, measure the flyback angle, 143 degrees, go back into our curves, and I already set that to 20%. You can adjust it for whatever your as-builts are. But now it's set. We've set the 160-20 based on the actual phase angles that the system returned. So what this does, now the software knows what your curve is. And when I go and find an indication such as this one, and I hit my max rate button, it gives us 100%. That's how we know how deep it is. Approximately. This is eddy current. It's not exact science. Then when I go to this particular indication and hit max rate, returns 60%. And then when I go to the 420s and measure it, max rate, I get 20%. So if I had a signal that came in about 120 degrees, let's say, where would that come up? Well, let's just follow the plot here. What does it say, 120 degrees? A signal with a phase angle of 120 degrees would be about 40%. We don't have a 40% in our cal standard, but if we did, it would be at about 120 degrees based on this as-built phase versus depth curve that